Welcome. We're about to embark on a study of work and energy. So let's just recap what we know from the junior school. What is energy? Well, energy, as we should know, is the capacity to cause change, and we often define it as the capacity to do work. We should know that energy has two forms. It is both kinetic and potential. And kinetic energy is the energy association with movement. If an object is in motion, it has kinetic energy. And we also know that energy is measured in joules. So there we are. Right, having a look at kinetic energy specifically now. We know that kinetic energy has some sort of velocity associated with it. So if an object has motion, has velocity, is changing its displacement, it must have kinetic energy. So here are four versions from your textbook which are kinetic energies. We've got good old translational kinetic energy, which is what we have as objects move in a straight line. That's the one that we are most familiar with. But we may not realize that sound is a kinetic energy because it is actually air molecules moving backwards and forwards. Thermal energy is the movement of atoms backwards and forwards. They're just oscillating backwards and forwards. Even though they're not actually moving great distances, it is still motion. And rotational kinetic energy is objects that are rolling, or spinning. They don't have to actually be moving. So a turntable, for instance, has rotational kinetic energy, even though it's not in motion, but the actual disc that is rotating has rotational kinetic energy. The formula for kinetic energy is given over here. It's quite a simple formula. It is a half mv squared. So let's have a look at I'll just rub that out because I need to run around it. So K stands for, obviously, kinetic energy. And it's going to be measured in joules. It is only measured in joules if the following conditions are met, that it's a half times this m, and the m here is the mass of the object in motion. Okay, and that must be measured in kilograms. If it's not measured in kilograms, then we can't measure kinetic energy in joules. The other thing here is velocity or speed. It doesn't matter in this case because we're going to square it, and we'll talk about energy in a few more moments being a scalar object anyway. And so this is either the velocity or speed. It doesn't matter. And that must be measured in meters per second. If it's not measured, if we don't have kilograms, we don't have meters per second, we can't define energy here being in joules. Right, so the last thing I want to talk about before we go on to potential energy is the third part, which is going to be new to us. We know that energy is the capacity to cause change and do work. It is potential and kinetic, and it's measured in joules. The final part is that energy is a scalar. So it's a scalar quantity. Making sure that I'm spelling it right. It's not a vector, even though velocity over here was a vector. It ends up that kinetic energy, or all forms of energy, are in fact scalar quantities. They do not have direction, they just have magnitude. Okay, so let's have a look at the other form of energy, which, as we know, is potential. So potential energy is the other major category, and it's defined as the energy associated with an object due to its position in a field. And there are three major fields that are of interest to us. It is the gravitational field, the electrical field, and the magnetic field. We should recognize that these are the three fields that we associate with action at a distance. So an object has potential energy as gravitational potential energy just because it is somewhere in a gravitational field. And when we come and study potential energy in a few more moments, in a couple of days, we'll be looking at specifically that gravitational potential energy. While we are here, it has a symbol, just like kinetic energy has the capital K, gravitational potential energy has the symbol U. So what are other forms of potential energies? Chemical energy. So chemical potential energy is because we move electrons from one atom to another. We are moving electrons from a lower state of energy to a higher state of energy. Elastic, magnetic, and nuclear are all different forms of potential energy, all because they are associated with one of these fields up here. Nuclear may be more to do with the strong nuclear force and the electroweak force. So what is work? Now, work is the capacity to cause change, just like energy is, but in particular, it is the change in energy. So work is a change of energy. So, right? Work is equal to a change of energy. So we have this over here. Okay. Work is done when a force causes displacement. So this diagram here has a gentleman pushing a box with a force of 30 newtons across 10 meters displacement. So because we are using a force and we are causing a change, a force causing a change is work. And in this case, the amount of work being done is quantified by this formula over here. So let's have a look at what we've got here. So here is our first formula for work. You'll see that there is a whole series of formulas for work. So work is given the letter W. Unfortunately, it is the same as the letter for weight. That's hence we don't normally use weight as W, we just use mg as its symbol. Work, being a change in energy, is measured in joules as well. And force there, this is the force that is acting, and that must be measured in newtons, and this is the displacement that it is going through, and that must be measured in meters. So work is the product of force and displacement. The other forms that work take, because work is defined as a change in energy, work is also the change in kinetic energy and also is the change in gravitational potential energy. I mentioned before that U is the symbol for gravitational potential energy. So having a look at this diagram here and going to calculate the amount of work this fellow is doing. So a person pushes this heavy box for 30 newtons through 10 meters. What's the amount of work done? Well, we know that work is equal to Fs, okay? Now this force is the net force. So with this fellow here, there might be 5 newtons of friction going backward, and that would mean that he would be pushing with 35 newtons forward, but the total force all up becomes 30 newtons. So it's the net force that we are applying here. So going over here, that means that the force that we are applying all up is 30 times 10 meters, and that's 300 joules. So he needs 300 joules to do that push. Sometimes we don't push or pull in the same direction that we displace. So this lady here is pushing that pram, and she's pushing down on the handles. So the handles are in that direction down there. But because of the way that the engineering of the pram is done with the wheels, we are getting a displacement in that direction. Now, the displacement with our formula for work equals force times displacement, these must be in the same direction. Okay, so it's only the one at the angle, the force at the angle can be converted into, or not converted, but can be resolved into its two components. It's that component and this component, okay, the yellow component and that pink component there. It's only the yellow component, the top component here, which is actually in the same direction as displacement. This part of the force, the F sine theta in this case, is not doing any work, because even though it is pointing down and it is a force, the pram is not moving down. It is not moving into the earth. So this is the only force causing work. Okay? So even though we have forces, two forces here, which are combining to a single diagonal force here, it is only the horizontal force that is causing work. The other force is doing no work. So in this case, if she's pushing with let's say she pushes with 30 newtons, just like that other fellow was pushing, and doing it at an angle of 30 degrees below the horizontal, then this would be 30, I've used 30 twice. Let's make that a different angle. Let's make it nicer. Let's make that 60 degrees. So this would be 30 newtons cos 60 degrees. And that would be the force that we would use here. Okay? Now, before we get on to the last thing I want to look at, just say you are pushing on a door. Okay, so here is our door. It's our door handle, and we are pushing against it. Okay, here's our 5 fingers. If we're pushing on that door and the door doesn't move, are we doing work? Work equals force times displacement. Okay, if I push with maybe 100 newtons on that door, but I do not move the door, my displacement is 0, therefore my work is 0. So work does require a change in displacement of something. If it doesn't displace, then technically we are doing no physical work. Right. The last thing I want to do before we do a worksheet is have a look at graphs that display force and displacement. So here we have the force displacement diagram, which is for this gentleman here who's picking up a box with 20 newtons. He's going to pick this box up and he's going to move it through a displacement of 1.2 meters. Okay, he's not going to accelerate, so it's just a constant force that he does. This force here is just the weight of that box, remembering that's just an action-reaction force, so we're not really considering that one there at all. Okay, here is a graph of that force. So it's 0 displacement at this point, so there is 0, and then he moves this 20 Newton force on this box through 1.2 meters. So that is what that force displacement diagram is. If we had a look at what the area is down here, the area would be found, so if I had a shape inside this box, inside this graph here, that shape's area would be measured in force on the vertical and displacement on the horizontal. So the area underneath here would be measured in Fs. We're multiplying a force axis times the displacement axis. So that means that the area under a force against displacement graph is the equivalent of work. We've seen a similar thing to do with this. The area under velocity versus time graph is displacement. So the area here, the amount of work he does, will be found by finding that area just there. So how much work has he done? Well, work would equal 20 newtons times a displacement of 1.2. So that would be the first way of doing it. You could do that, 0.2 times that. I'll just get a calculator and do that. So it's 20 times 1.2, that's 24. So 24 joules. So that's the first thing we could do. We could just use the formula. Or we can simply use the area here, which is 1.2 along there, and this is 20 up there. And therefore, the area here is 24, and therefore it's 24 joules. Notice the area is the product of these two numbers, which is what we've got over here. Moving on, what happens if we don't actually have a force displacement diagram that's a nice box? Well, here we have a triangle. So this one here is the force pulling a spring to stretch it. So the area under a force displacement diagram is, remember, it's force over here and displacement on that one. The area under the graph, that would represent work. Okay? So here we haven't got a nice, force equals displacement times force, because it's not a horizontal, it's not a constant force. So we're going to simply use the idea that work equals the area, which is a half base times the height, being the triangle. So it's a half times the base. Now, this is going up in 0.002, so this number here would be 0.016. So that's 0.016 times the height, which is 200 newtons. And so typing that in, you get 0.5 times 0.016 times 200, and you get 1.6 joules of work is done. Right, you'll be doing a worksheet now. It's worksheet 4C1 called Work, and you'll find the link to that on Compass, and there will be a video going through the worksheet with you, just in case you have any difficulty. Okay, I'll see you on that video.